Okay. Chapter 13 is about the NMR, or nuclear magnetic resonance spectrometry. The application for this technique is being able to determine structural formula and hydrogen distribution. Basically, that's like very powerful technique, is a lot more powerful than the IR. IR would give the functional group. NMR can give functional group, and it can give also the hydrogen distribution. Still, NMR still by itself is not going to be enough in order to determine the structural formula, because even though you know the functional group, you know the hydrogen distribution, you need to know more precise value for the molar mass. So you do need the mass spec at least. So NMR plus something else can be used in order to determine the structural formula for an organic molecule. The NMR is used for, just move these, I can see them. So your molecule must have one of the following elements with a odd number mass or odd number of proton, odd number mass. So we have the or atomic number or odd number mass. So these are the popular ones. They can do NMR based on proton NMR, which is the hydrogen 1, carbon 13 NMR, and these two are more popular. And the most popular one is a proton NMR or hydrogen 1 NMR. Carbon 13 NMR can also be used. It is used more often than nitrogen, fluorine, and phosphorus, but it's just showing the point that if you have an odd number mass, if the molecule contains an atom with odd number mass, can be used and recognized in the NMR machine. So if you have a nucleus with odd number, odd atomic number or odd mass number, it can have nuclear spin. So as it is spinning, the spinning of the charged nucleus, it can create magnetic field. So when it does create a magnetic field, that magnetic field now can be placed in a external magnetic field. So your molecule generates magnetic field. Then the sample is placed inside in a sample holder, and it is exposed to external magnetic field. Now, if you have the external magnetic field, the external magnetic field is going to be a lot more stronger than the magnetic field created by the molecule. So external magnetic field is going to dictate what should be the direction of the magnetic field created by the atom in your molecule. So the magnetic fields, after they are aligned, created by the molecule, is going to be aligned with the same phase as the external magnetic field or the opposite. So if you have the same phase, for example, or the opposite, now these two, they have like a alpha state or beta state. So you have an alpha spin state and you have a beta spin state. Alpha, by convention, aligned with the external field, and beta would be the complete opposite. So these two are the possible state for the magnetic field of your molecule when it's exposed to external magnetic field. Now, after you have these two states, like this is the case that your molecule, before being exposed to external magnetic field, the magnetic field by the molecule was generated, and they can move in any direction. There is really no specific direction for them because they are moving freely. There is no force outside saying which way to go. But when you place that within the external magnetic field, there is a force. It's saying there's only one direction allowed, straight up and down. Okay, so either aligned with external and name yourself alpha, or be opposite to it and name yourself beta. So let's say half of those is going to go to the alpha and some go to the beta. Then this magnetic field is going to, so when we have them as aligned with or against with, there's a difference in energy. There is an energy difference between alpha state and beta state. When the analysis of the sample begins, the machine is going to change all of these beta state to alpha, or vice versa, because it's the same. It's going to be the same amount of energy, because we are looking at the change in energy between the energy of the beta state to the alpha state. So since you have the change in energy, that amount of energy is going to be required to go from alpha to beta, or from beta to alpha. And to move from alpha state or beta state, energy is required. That amount of energy is going to be calculated by the detector of the NMR machine. Now, remember the different parts of the spectroscopy technique machine. There were like 4 major parts. You have your sample holder. So you have your sample holder that contains this alpha state, beta state. You have your external magnetic field. That's the energy that is applied, the source of energy. Then you have a detector. You have a detector, and then you have, after the detector, you have a recorder. Now, the detector is going to detect how much energy is needed to go from alpha to beta state, and the recorder is going to record that value. The good thing about the hydrogen in different chemical environment is going to require different amount of energy. So when you have a point of difference, then that amount of energy is going to be different. The machine or the NMR detector can detect what type of hydrogen your compound contains, and the hydrogen is coming from which functional group, which functional group is present in the molecule. So it's going to give you signals. When you get those signals, and if you have a table to compare those signals to, then you can decide if you have what type of hydrogens you have. So just before looking at the signals, you could have the magnetic field 300 megahertz. That's basically the frequency. We could have 400 megahertz, 500, 600, and 700. The more megahertz of the field, the more expensive the machine is. Okay. Now, the amount of energy needed to take from the magnetic field of the atom from alpha state to beta state for different hydrogen, the amount of energy is different. And what we call different hydrogen. Let's say you have hydrogen that is attached to carbon only, and then you have another carbon here. The electronegativity of this carbon is not higher than the other carbon, so they have same electronegativity. Electronegativity of carbon and hydrogen also is very similar. So these hydrogens are kind of, is known the term shielded in NMR, but if you do have a hydrogen that is attached to a CO double bond, okay? So if you have a hydrogen that is attached to CO double bond, what's going to happen here, that oxygen has higher electronegativity, so it's going to give positive charge to this carbon, and if this carbon is positive charge, it's going to pull some electron from the hydrogen. So this hydrogen is in term is called de-shielded hydrogen. So this hydrogen is shielded. That means electrons are around it. Electron is moving around it. It's one electron, but is moving around the nucleus. It's shielded with the electron. But this hydrogen, electron is being pulled away from the hydrogen. And this hydrogen is known as being de-shielded hydrogen. Now, what's going to happen in NMR spectrum when you get a signal, you will see that you have signals in different location of the NMR. Let's say if you have a 0 here and 10 here, and you have like internal standard, and that is known as the TMS. With the TMS is the most shielded hydrogen because Si has lower electronegativity compared to carbon. So it's not going to remove any electron from this carbon. So this carbon does not feel positive and is not going to remove electron from hydrogen. And this is the lowest electron attraction by another atom compared to the hydrogen from this carbon. So the term is called, this is the most shielded type of hydrogen. Since it's most shielded, it can be used as a reference. And that reference, it shows a peak at 0. And this compound as internal standard is always added to the sample that you are analyzing with NMR. So when you are analyzing your sample with NMR and you add the TMS or the internal standard to your compound and you get your spectrum, we know that there would be one signal at 0, and we know that signal belongs to TMS. Now, other hydrogens are going to be compared to this reference, to this hydrogen of the TMS. The hydrogen from this OH is de-shielded or less shielded. And because it's less shielded, is going to be, because this is most shielded, right? Shielded. So we have this one is shielded. Anything that is de-shielded, it would appear to the left of this TMS line. The more de-shielded it is, the further away is going to be from this 0 signal. So if we look at like OH is going to appear here for OH. But if you look at a COO hydrogen, aldehyde, okay, aldehyde would appear between 9 and 10. So if this is 9, that's 10, the aldehyde hydrogen would appear here. If you have a carboxylic acid, it's not even on the scale of 0 to 10. It's called like out to scale between 10 to 12, or sometimes they say, some books, not people, some books, they would say 10 to 13. So I would just go with the 10 to 12. If you have a carboxylic acid, would show at a signal between 10 to 12. So if we know that presence of aldehyde is determined by the location of a peak between 9 and 10, you get your NMR spectrum, and then you have 9 and 10. There is a signal here. This compound, whatever it is, it has aldehyde functional group. If we know that a compound with the COOH is going to have a peak between 10 and 12, so you get another spectrum. You see that you have some signals here, and also there is a 10 to 12 here out scaled, and then there's a peak between 10 and 12, then we know for sure this is a carboxylic acid. So if these values are constant and is consistent with the functional group, is a lot of detailed and very good information, because right away, if you look at the spectrum, it says, okay, there is a peak between 9 and 10. What does it mean? A peak between 9 and 10, what does it mean? I just want you to repeat it. So we know that that's how you learn and that's how you memorize it. A peak between 9 and 10. What does it mean? It means that is okay, is going, I'm going to have to close that. Very good. If, you have another compound, the spectrum, NMR spectrum for a compound, that there is a peak between 7 and 8. So between 7 and 8, you have a peak, or you have like a crowded peak. And what does it mean? You may not know it now, but within the next 5 minutes, you will learn about this new peak, that any compound that has a signal between 7 and 8, it is aromatic. So that's good piece of information. So if you get like multiple choice question, and just like similar to the quiz questions you had for for chapter 12, that we already, reviewed the quiz together, see that you get a spectrum and you want to know which compound does it belong to. So you can eliminate your choices. There is a peak between 7 and 8, so there must be aromatic. That compound must be aromatic. And if it doesn't contain a benzene ring, it's out, is eliminated. You have a spectrum that has a peak between 9 and 10, then it's aldehyde. Anything that is not aldehyde or doesn't have aldehyde functional group is eliminated. If you have something with carboxylic acid between 10 to 12, then we're out to scale. Then we know we have carboxylic acid. So any choice that is not carboxylic acid is being ruled out. Okay, what other information do you get from the NMR? Number of signals. So if you have number of signals, is going to show the different type of hydrogen. With the example of the methanol that we have there, we have 2 types of hydrogen. This is if these are called hydrogen A, this would call hydrogen B. So we have 2 types of hydrogen. So if we do have NMR spectrum, this TMS never counts. Okay, it never counts. So from 0 to 10, if we will have a signal between like around 3.5, because we have this oxygen pulling electrons from the hydrogen. So, and then we have a peak, like a broad peak, anywhere between 2 to 5 for B, because it's OH. Again, is broad, and is short, is broad. Why is broad? Because of hydrogen bonding. Why is short? Because the height of the peak for NMR is going to, that's the intensity. The height of the peak corresponds or correlates directly with number of hydrogen of that type. So we have the OH here, and then the other one is like a CH3. So we get 2 signals. Number of signals, it shows how many different type of hydrogen we have. Location of the signals, it corresponds like how shielded or deshielded the proton is. Intensity, as I said, the height of the peak, which usually it shows with a like a blue color. It means it shows the intensity correlates with the number of hydrogens. So if we have 3 hydrogens in the CH3, then we have 3 to 1 height ratio and 1 hydrogen for OH. So this height ratio is going to be 3 to 1. This blue line is called as like a integrated line, and the integrated line, it shows the intensity, and it's usually the height of the vertical line that you are looking for. So is this height here and this height here that counts. So if it's a 3 to 1, that means for every 1 hydrogen of OH, you have 3 hydrogen of the other type that you have. So we get like a lot of good information. Number of signals shows how many different type of hydrogen you have. Location shows how shielded or deshielded hydrogens are. Intensity shows how many of that type of hydrogen you have. And then the splitting pattern shows that how many protons you have on adjacent carbon. The component of the machine, is sample holder, which is this test tube here. The source of energy, which is the magnetic field in this case, external magnetic field, is very strong. And if you look at this silver big cylinder that we have on the picture down there, that generates the magnetic field. Then you have a detector and you have a recorder. The magnetic field is very strong for NMR, that if you walk into NMR room, they say make sure you leave your credit cards and any electronic keys out, because you don't want them to be wiped out. So for the example of methanol, we have two types of hydrogen, the blue ones, which is the type A of the hydrogen, and the red one, which is B. You have two locations for that. They are not same, they don't have same degree of shielded or de-shielding effect. So hydrogen attached to carbon, and then you have the hydrogen attached to the oxygen. Which one is being more de-shielded? Why? Because it shows that this is the TMS and is the most shielded. So the red one is more de-shielded, or out of these two is most de-shielded. Can you tell me what makes the red one more de-shielded? What factor affects this shielding effect, or what makes the hydrogen attached to the oxygen to be more de-shielded? How is de-shielded? How is that hydrogen being de-shielded? What does it mean is being de-shielded? Shield, it's like, in everyday talking, shield is like layer of protection, right? Layer of protection. So when we say shielded in the NMR term, shielded means that it has more layer of electrons. Electrons is covering that nucleus. Now, if you have electron withdrawing group, okay, if you have electron withdrawing group, next to it is going to remove electron or pull electron away from nucleus of hydrogen, and it makes the hydrogen, as Anna responded, is more exposed or naked of electron, so is de-shielded. So red hydrogen is more de-shielded than blue hydrogen. Can someone respond? Why is that? Why red hydrogen is more de-shielded than blue hydrogen? What do you think? This is like electrostatic effect, right? Or electronegativity of oxygen. Oxygen is the only one that is going to de-shield the hydrogen, the blue one and the red hydrogens. Oxygen is the one that is de-shielding. So further from carbon or further from, if you revise your answer, it's going to help everyone who's watching that also. Revise it, please. There is the distance effect here, but which one is further away from what? And you could use the blue color or red color. Blue hydrogen versus red hydrogen. Why red hydrogen are more de-shielded? The red hydrogen is closer to oxygen. Oxygen has higher electronegativity. Oxygen is the one that is pulling electron. When it comes to the blue hydrogens, oxygen pulls electron from carbon, and then carbon becomes slightly positive and pulls electron from other hydrogens. So this is like a secondary effect. But from the red hydrogen is a direct effect. So how close is the hydrogen to high electronegative element? It's going to affect how de-shielded that hydrogen is going to be. Does it make sense now that the red hydrogens are more de-shielded than the blue hydrogen? because red hydrogens, they are directly affected by the oxygen, or directly losing electron to oxygen, the red ones, okay? Red hydrogen directly losing electron to oxygen. But the blue hydrogens, they are being affected by carbon that is attached to the oxygen. So it's a direct effect. That means red hydrogens are more deshielded, so they are further away from TMS compared to the blue ones. Blue ones also are deshielded, even though they are not directly attached to the oxygen, but they are still deshielded, but they are not as deshielded as the red one. And the TMS, the internal standard, it shows a peak at 0. So anything that if it's more deshielded, it would be further away from TMS. Less deshielded, it would be closer to TMS. But you don't have anything more shielded than the TMS. TMS is the 0 line, and everything else is going to be compared to TMS. Let me know if you have any questions. Okay, so if you buy a machine that is 60 megahertz magnetic field or 300 or 700, the spectrum is going to still be for all of them. The spectrum or the scale on the spectrum is going to be from 0 to 10 and then 10 to 12 out the scale, which is for carboxylic acid. Okay. Because these are all comparing to the, so basically the ratio is used. So the ppm is from 0 to 10. This is the chemical shift, and you're comparing everything to the TMS. But the stronger the magnetic field is going to be, the more accurate and more sensitive it's going to be. That means the sample size that you're going to use is going to be smaller. You can use a smaller sample size for the stronger or high resolution machines. High resolution machine, that means they are more expensive. And how do you know? One of the characteristics of that would be a stronger magnetic field. But regardless of the size of the magnetic field or the magnitude of the magnetic field, is going to be, the scale is going to be 0 to 10. If a compound shows a signal for the first machine that had the magnetic field is 100 megahertz at 6, and if is 300 is going to also show at same location 6. Okay. Information that you need for the exam. Know the location, approximate location for every type of hydrogen. So basically memorize this table. It's not a huge table, but it requires some memorization. If you have an alkane, a CH3, this is a primary carbon. If it says CH3 and alkane is a primary, that means that is attached to, let's say if you have a CH3 here, CH2, CH2, and then CH3, means that is attached to one other carbon, so this is a primary. And if you take out that and I add a CH3 here, this carbon is a secondary carbon. This carbon is a tertiary carbon. So this hydrogen is a primary hydrogen. That hydrogen is a secondary hydrogen, and a hydrogen attached to tertiary carbon is going to be tertiary hydrogen. So if you have a alkane, the CH3 of alkane, it would show a peak at 0.9. This is a CH3 of alkane, not CH3 of ether or carboxylic acid or others. They're going to be slightly higher, but if it's a CH3 from alkane, CH2 from alkane, which is like this one, it would show a peak at 1.3, 1.2 to 1.3. And if it's a CH, that means a tertiary hydrogen, it would show a peak at 1.4. These are approximate numbers. if a CH3 attached ketone functional group is going to be shifted to higher number. Remember, electron withdrawing group is going to increase the frequency, and in this case is going to increase the ppm value. So if CH3 attached to electron withdrawing group is going to shift to 2.1 rather than 0.9. So it's shifted by 1.2, right? It's shifted by 1.2 plus 1.2. Why? Because of this group that we have, the CO double bond. What counts as electron withdrawing group? Electron withdrawing group and the pi system, they are going to deshield, have deshielding effect. The factors that have deshielding effect, one is electron withdrawing group, and second is the pi system. So if you have a CC triple bond, you do have a pi system. A pi system is going to, it has a strong deshielding effect. So it's going to deshield this hydrogen, and hydrogen would show at 2.5 instead of the 0.9. So if you have an alkyne, the CH would show at 2.5. Electron withdrawing group. So this is the pi system. So you have the pi system, and you have electron withdrawing group. Electron withdrawing group. Both of them have deshielding effect, pi system and electron withdrawing group. If you have one halogen attached to it, instead of showing a peak at 0.9 or 1, it's showing between 3 and 4. What do you have down here? Is electron withdrawing group or the pi system? For vinyl hydrogen is the pi system. And if it's a vinyl hydrogen, is going to show a peak between 5 and 6. Do you see this pattern? I mean, I'm trying to help you to memorize it so you don't have to memorize everything. So if you pay attention to this, like choices of pi system and electron withdrawing group, and be able to see, visualize it, okay? You have a pi system, it's going to increase the value for delta, or the approximate delta is going to go up. You have a pi system here. You have electron withdrawing group here. You have electron withdrawing group here, and this number is increasing. What do you have in here for allylic? You have a pi system, but is indirect effect, is not direct effect like vinyl, because you see if it's a direct effect like vinyl, this is going to appear between 5 and 6. But if it's indirect, because you do have a carbon-carbon bond in between, it's going to be shifted to higher number. But if you're comparing to 0.9, it's going to be higher number, but it's only added like 0.8 because it's an indirect effect. It's not directly on the same carbon. The carbon-carbon double bond is not on the same carbon. It's adjacent to that carbon. And then what is this pH? pH stands for phenyl group. Phenyl group is like a benzene ring that has lost one hydrogen. So if you have this hydrogen here, this is the phenyl H. So phenyl is the benzene ring. Is a pi system again, is a strong conjugation going on here, and is going to remove is going to increase, I'm sorry, is going to increase it to 7.2 if it's directly attached to the benzene ring. But if it's not directly attached to benzene ring, what would be if it's not directly attached to the benzene ring? Let's say you have benzene ring here, then you have a CH3. Okay, then you have a CH3. This is not hydrogen directly attached to the benzene ring. It's directly attached to carbon that is attached to benzene ring. And that is like indirect effect. So you see that pattern again. So this is like a 2.3. We had similar situation here for indirect effect. If it's directly on the carbon-carbon double bond, hydrogen is directly on carbon-carbon double bond, which is the vinyl group at between 5 and 6. If it's indirectly, 1.7. Directly, 7.2. Indirectly, 2.3. This type of hydrogen, this is known as the benzylic benzylic hydrogen. So we have the benzyl group, okay? Benzyl group. Aldehyde, 9 and 10, very easy to remember. Aromatic, between 7 and 8, very easy to remember. Aldehyde, 9 to 10, and then carboxylic acid is going to be between 10 to 12. So these are very easy to remember, the purple color. OH and NH is going, there's no fixed place for that, anywhere between 2 to 5. It can be NH or OH, but the characteristic for that is that it's going to be a short and broad peak. This is for both OH and for NH. Aromatic alcohol is going to show a peak between 4 and 7, aromatic. But how would you know you have aromatic? Because this is going to also be short and brown. So you must have a peak at 7 to 8 for aromatic. And then you have a peak, let's say at 4.5. Then we know that this is coming from OH that is attached to an aromatic ring. Questions? There's a lot of information on this slide, but I want to make sure that I answer your questions before I move on. Do you have any questions about this? Yes, memorization is involved, but if you follow what I'm saying now, it's going to make it easier for you to memorize it. If there is no questions, you may just say it in the chat area, no questions, and I can move on. Any questions? No? Okay. Electron withdrawing group is going to increase. Oh, so if we have CH4, that's the smallest or the first family member of the alkane. If it shows a peak at less than 1, when you add one Cl group to the same hydrogen, so to the same carbon that carries the hydrogen, this is like a direct effect, is going to move to 3. That's like it's moving 2.5. Now you add a second carbon, these hydrogens would appear at 5.3. You add a third chlorine, the more electron group that you are adding to this carbon, that de-shielding effect is going to increase, and the signal would appear at a higher number. So the most effective one was the first chlorine that you're adding, because it's already being de-shielded. So adding a second chlorine is going to de-shield more, but it's not as significant as the first one. The first one is like a very sharp. Of course, yes, good question, Mohammed. If you have like a fluorine, the higher the electronegativity, the higher the de-shielding effect. And also the numbers, how many halogens you have. More number of halogens, the higher the de-shielding effect is going to be. Okay. So a lot to memorize from this table, and I hope that you do it. So a pi system, it counts as electron withdrawing group for alkene, for alkyne, for aromatic, and then electron withdrawing group. Aromatics, hydrogen that is directly attached to aromatic ring would appear between 7 and 8, and is going to be very crowded peak. So you want to, for aldehyde between 9 and 10, these are like very specific. Alkyne at 2.5. Carboxylic acid. How do we know we have carboxylic acid? If you didn't have this molecule here, it says 2 ppm offset. What it means that this signal appears at 12. So basically, if the scale was 0 to 12, this signal would appear at 12. And if it's out of scale or offset, that's the only functional group that's going to be offset is going to be carboxylic acid, and that belongs to the OH. You only have two types of hydrogen here, so you're only expecting to have two signals. Other than the TMS, TMS does not count. It's going to be there all the time. This CH3 now is attached to a carbonyl group. It usually, if it was an alkane, it would be at less than 1 or 0.9. But since it's attached to electron withdrawing group of carboxylic acid, it has shifted to a 2.1 or 2.2 unit. So it's going to shift to higher number. The height ratio, it shows the ratio between the hydrogens. So if you have only two types of hydrogen here, CH3, and then we have T-methyl group and a T-butyl group. So we have a methyl group here and T-butyl group. T-butyl group has 9 hydrogen. Methyl group has 3 hydrogen. So the height ratio is going to be 9 to 3 or 3 to 1 ratio. 9 to 3 ratio or 3 to 1 ratio. This is the height ratio. So you can also see the shielding and the deshielding effect. This oxygen is directly attached to the carbon with the CH3. So deshielding effect is more significant. The oxygen is indirectly attached to the carbon that it is attached to the other CH3s. So this is not less than 1 as is expected because it's CH3, because it's indirectly attached to oxygen. It's a higher number. So anywhere between like 1 to 3 or 1.3, 1.4, but is going to be higher number. So when you look at the molecule, first of all, you need to recognize how many different types of hydrogens you have. Let's say if you have a molecule that is just a simple molecule and is CH2, CH3. How many different types of hydrogen do we have in this molecule? In this molecule, how many different types of hydrogen we have? If I call these hydrogens A hydrogen, the CH2 is going to be A hydrogen or B hydrogen. Is CH2 similar to CH3? Are these chemically the same based on the environment? Are they the same type of hydrogen or they are different? Remember, we had a primary. This is a primary, this is a secondary. So if this is an A type, then the secondary is going to be B. But this primary is going to be A because these are very similar to one another. So we have two types of hydrogen. The ratio between the A and a B is like 6 to 2 or 3 to 1. Okay? So if I was going to draw a small NMR here, and if I call this a TMS, and then I have like a 1, and then I have 2 here, the CH3, what location would the CH3 appear? Between 0 and 1 or 1 and 2 for this molecule? If you remember from previous slide, the CH3 from alkane, it was at 0.9. So I'm going to have a peak here, okay, for the CH3. For CH2, it says that it was a 1.3. So I'm going to have a peak at 1.2, 1.3 here. When I'm drawing these peaks, I'm very careful with the height of the A-type hydrogen and the B-type hydrogen. So these are the hydrogen B and this is hydrogen A, because the height ratio, it shows the ratio of number of hydrogens also. So if the height ratio of hydrogen A to hydrogen B is 3 to 1. I have to also be careful with the height ratio. How many different hydrogens we have for compound A? How many different? Two. So we have A and we have B. What's the location for A? Location for hydrogen A? What type of functional group is this? This is a carboxylic acid. And location for carboxylic acid hydrogen is 10 to 12. The location for CH3 that is attached to a CO double bond is at 2.1 because of this electron withdrawing group. Otherwise, it would have been at 0.9. For the CH2, we have three types of hydrogen here. If I say this C is going to be around 1, the CH2 and this CH2, are these both at the same location? Are they similar? Which one would be at higher number? Let's just answer that question. A or B? Which one would be at higher number? A. A would be at higher number, and let's say if this is at 3.5. Why is that higher number? Because A, the carbon that is on A, is the hydrogen that is on carbon A, that is directly attached to the Cl, but B is indirectly attached to Cl. So this can go to like 1.5, going from 1.3 or 1.2 to 1.5, but this one directly affect and is going to go to 3.5. And the CH3 is like too far away from the Cl and is not going to be affected by it. It's like it usually goes by like 3 bonds. So if it's a 3 bonds, this is like a 4th bond is not going to count, is not going to be affected. So this would be around 1. For C, we have a CH3 that is attached to another carbon. So this is around 1, between 0.9 and 1, okay, around 1. And then you have a CH that is a vinylic CH. So if you have a vinylic CH, it's going to be between 5 and 6, right? So we have vinylic, and it's going to be between 5 and 6. So you have to recognize how many different types of hydrogen you have, and you have to predict the location. You do have a table that was shown in the PowerPoint, and you have it in the book. You can reference that for all homework and quiz assignments. And for the exam, hopefully by then you would memorize most of it. Questions. The height ratio, integration line, we keep talking about it. The integration line or the height ratio is corresponding the ratio of the hydrogens of the type. So if you have like a 9:3 or 3:1 ratio, that should apply. Sorry. A splitting pattern. If the hydrogens are not equivalent, they would split each other. That is, it shows basically how many hydrogen you have on adjacent carbon. So we have 2 types of hydrogen, hydrogen A and hydrogen B. One hydrogen A, you have 2 hydrogen A. So the height ratio is going to be 2 to 1. So if this is like for hydrogen A, the height for hydrogen B is going to be double. It's not shown in this because it doesn't show, but I just want to emphasize it. Now, prior to this slide 19, I was just showing one peak, okay? Just one triangle, one peak. Now it's basically emphasizing that you have split it, two peaks. So it's like a doublet, and this one is like a triplet. So you have basically that pattern for this one. Where is that pattern coming from? The rule is n plus 1. So if this is a triplet for hydrogen A, that means on adjacent carbon, you had 2 hydrogen. And then 2 plus 1 is 3. So it's the n plus 1 rule. You're looking at this hydrogen A because it's more de-shielded because of the 2 bromine that you have is further away from TMS. And is going to be split by 2 other hydrogen. So it's n plus 1. N is the number of hydrogen on adjacent carbon plus 1. So we have 3. So the peak is going to be triplet. Hydrogen B. These two do not split each other because they are on the same carbon and they are identical. But they are split by hydrogen A. Okay. Hydrogens B are split by hydrogen A. How many hydrogen A you have is just 1, and that is the value for n equals 1. So for these, n equals 1, so it's going to be 1 plus 1 is 2, so the peak is going to be a doublet. So it shows a splitting pattern. How many hydrogen you have on adjacent carbon? So when there's a splitting pattern, you could have like a singlet, okay? Singlet, then you could have a doublet. When you draw a doublet, the height of the 2 peaks, they are almost the same. When you draw a triplet, it's going to look like this. You have the one is, you see, is an odd number triplet. So for a triplet, you have one that is maximum and the other 2 are like minimum and 1 on each side. For quartet, you have this pattern, looks like this. Is an even number, then you have 2 of them that are on the maxima in the center. Everything else is going to be like lowered like a tree, like a Christmas tree. So you have for 5 is going to be 1, 2, 3, 4, and 5. So you have odd number, only 1 that is going to be up. For 6 is going to look like this. So you have 2 that are same height and they are the highest. And then the other ones, they're going to just, this is not like the best one. Let me see if I can just get the last part and draw it again to mirror it to the other side. Oh, doesn't want to be mirrored, but it's going down this way, like a tree. So what does quartet means? A quartet means that the hydrogens are attached to 3 hydrogen on the next carbon. So let's say if I had the same molecule that I had before, a CH3, CH2, CH3, what would be the splitting pattern for this CH3? The splitting pattern for this location is going to be 0.9, and the splitting pattern, how do we know the splitting pattern? You look at the adjacent carbon. There are 2 hydrogens there, n equals 2. So 2 plus 1 is going to be 3. So it's going to be a triplet. For hydrogen B, if this is hydrogen A, for hydrogen B, location is going to be 1.2. What is the splitting pattern for B? Singlet, doublet, triplet, quartet, or quintet? Quintet, which one? Or more? Okay, good start, because if we count for hydrogen B, if we count only the hydrogens on the right side, that is a 3 plus 1, that would be quartet. But we said neighboring hydrogens, not the neighbors on the right side. This could be neighbors on top, neighbors at the bottom, neighbors at the left side as well. So we have 3 hydrogens here, and we have 3 hydrogen on the other side. So it's going to be 3 plus 3, that's n, and then n plus 1 is the 6 plus 1, and it's going to be 7. So we do have a septet for this one. For the CH2, it's going to be septet. So it's going to be 1, 2, 3, 4, 5, 6, 7. So for this, what about the CH3 on the left side? Location is going to be 0.9, and since it's attached to CH2, it's going to be a triplet. So if I have A and B, they are coming from same hydrogen, A, and then B, this is going to overlap. So it's going to appear in the same location. The only difference is that the height is going to be higher. The intensity is higher. So hydrogen, the peak A and a peak B is going to be combined. So A plus B. Same location, intensity would be higher. So the coupling, it's not observed between hydrogen 1 and hydrogen 4. It does observe between hydrogen 1 and if you had something on this carbon. So it goes to 1, 2, 3 bonds away, not 4 bonds away. Okay. So this hydrogen that we have is going to be splitted by hydrogen A, but not hydrogen 4. So it would be splitted by this hydrogen 1, split by hydrogen A. But hydrogen A is going to be splitted by hydrogen 1 and hydrogen 4 because it counts both sides. Questions? Okay, the hydrogens on CH3, these hydrogens are only affected by CH2. So the hydrogen on CH3, if I call this A, and that is A, is going to be triplet because you have 2 hydrogen. It doesn't mean that you have 3 hydrogens for CH3, but it means that you have 2 hydrogen plus 1, and that is the n plus 1 equals 2 plus 1, and it's going to be a triplet. That's what we have, a triplet for the CH3. For CH2, we have 3 hydrogen on the right side, but no hydrogen on the left side. Be careful with this. When you have a benzene ring, there is a hydrogen on each carbon, but when you have a branch, like alkyl group here, you have to remove this in order to add the CH3, CH2. So there is no hydrogen here. So it is only 3 hydrogen, and it's going to be 3 plus 1, that is 4, that is the n plus 1, your n plus 1, 4, and it's going to be quartet. Hydrogens on a benzene ring they all appear between 7 and 8, and they overlap each other like multiple times. And usually you get like a very crowded peak between 7 and 8. If you want to separate these and see exact pattern, you have to use a high resolution NMR in order to like magnify it. You kind of have to separate it in order to see, like, it does give you a helpful information. If you have like a dye substituted, is it going to be ortho, meta, or para? But if we can, you know, we have to be able to magnify it. If it's all overlapping and very crowded, it's not easy to interpret. But definitely, if you have a peak between 7 and 8, your compound is aromatic compound. Okay. When you have an isopropyl group, so you have isopropyl, you have 6 hydrogen that is going to split this 1 hydrogen. And then this 6 hydrogen is going to be split by this 1 hydrogen. So hydrogen B is going to be a doublet, and hydrogen C is a 6 plus 1, that is 7. So you have a septet. But the height ratio, this is representing just 1 hydrogen, is going to be very small. So if you see like a short and crowded peak, suspect to have a isopropyl, especially if you see a doublet next to it. Okay? So we have like a short and very crowded, but if you magnify it, you see that is a septet. And then you have a doublet that shows that this doublet is coming from the CH3s attached to the isopropyl. And then your other CH3, it shows a peak over 2 because it's adjacent to CO double bond. This is going to be, why is it singlet? It shows a singlet here for A. Why is it singlet? What does it mean that is singlet? It means the N plus 1 here is 0 plus 1, and that is 1. There's 0 hydrogen on adjacent carbon, no hydrogen on adjacent carbon. So 0 plus 1 is like singlet. Okay. I don't want to rush through the chapter. We are going to continue on this chapter next time.